Now that we've talked about dry friction, or at least the beginning of it, let's do an example of two boxes slipping on each other. So let's say example. Two boxes slipping. Alright, so let's draw our boxes. We have a small box sitting on a big box. That's our small one sitting on a big one. And the big box is sitting on some kind of a flat surface. Not smooth, but supposed to be a straight line. We'll say that there is the same coefficient of friction between the lower box and the ground, and same as between the two boxes. So both of these are mu s. We'll say the top one is box A, so this has a weight of A. This one has a weight of B, not another A. And then we want to find out what the strongest forces we can pull at PB, so at box B and at box A, to not have either of the two boxes move. So of course what we'll have to do is we'll have to do a free body diagram for each of them. So let's do the bottom one here. That's my box. And what do we get? Well, we know that we'll have a weight. Let's put that in here somewhere. That's my weight B. Of course, I have my force. That would be PB. And now let's look at the bottom where we cut away the ground. We'll have a normal force. We'll call that normal force NB, and which means it's a rough surface. So we'll have a friction coefficient, or a friction force there too. Now this box is being pulled to the left, so the force has to be acting to the right. FB. And now how about the top? Well, we have an NB, where we took away box A. So we'll call that NAB. And now we have to think about the direction of the friction force. To do that, I think we'll draw our little one first. Maybe it's easier. All right, because we know they have to be opposite from each other. So we know we have a WA. We have a force PA. And what else? Nothing on top, so the only we have of course NAB. NAB. And now this is maybe easier. We know that the small box is going to be sliding towards the left on the top box. That means here we'll have to act in this, not up there, wrong location. Have to be acting in this direction. That'd be my FAB. Of course, if it's acting to the right here, then it has to be the opposite direction there. So with that, we have all of our forces in place. And now we can go ahead and we can solve the system. So we have how many unknowns? Let's see. If we start down here, we have 1, 2, 3, 4, 5. We have 6 unknowns. Problem is we only have 4 equilibrium equations, right? Because we don't have any dimensions, so there's no moments. That means we need 2 more. Now the good thing is that we know that the 2 contact surfaces, the one between A and B and the one between B and the ground, of course have to be at impending motion for the strongest forces, right? Because if we pull just a little bit stronger, then we'd move. So we can say both contact surfaces are at impending motion, which means we can write that FB is mu s times, oops, that doesn't look right, mu s times NB, and FAB is mu s times NAB. So now we have 6 equations and 6 unknowns, and we can go through and solve this system. Let's think for a second how we do this best. Well, if we look at the small box first, right, then we could use sum of forces in the y direction to get NAB. Once we have NAB, we have FAB, and we have PA. Okay, let's do that. So we can say it has to be capitalized, for box A, sum of forces in the y direction equal to 0, equal to minus WA plus NAB. That means NAB is equal to WA. That means at impending motion, right, I know that FB is mu s times NAB. This should be an AB in there. Is equal to mu s times WA. All right. Now, if I do my sum of forces in the x direction, sum of forces in the x equal to 0, I get minus PA plus FAB. That means PA, which is one of the things I'm looking for, is equal to FAB is equal to mu s times WA. Yeah, I think it makes a certain amount of sense, right? That doesn't matter what the box at the bottom does, only depends on the top box, this force. All right, that was my small box, so let's go with a big one at B. So we can say for box B. For box B, what do we get? Let's see. Now we have NAB, so we can do the same thing. We'll do first in the y direction and then in the x direction. Sum of forces in the y direction equal to 0 is equal to minus NAB minus WB minus NAB minus WB, and then plus NB. Plus NB. That means NB is equal to WB plus NAB equal to WB plus, where's my NAB, plus WA. All right, does that make sense? Let's see up here. Yeah, it makes sense, right? That the normal force at B would be just the weights together. Nowhere else to go for the weight. All right, so that means, of course, that FB is just mu s times NB because we're at impending motion, which is the same as mu s times WA plus WB. And then we can look in the x direction. So we have the two friction forces to the left and the force to the right. Fx equals 0, so we have minus FAB minus FB plus PB. All right, solve that for PB. PB is equal to FAB plus FB. FAB was mu s times WA. And the other one we have right up there mu S times WA plus WB. So I can pull those together. That'd be mu S times 2 times WA plus WB. And there we have it. All right, that means based on this very simple setup, we can find the two forces, the two maximum forces that we could apply to box A and to box B without them actually starting to move.